Hello everyone, this is Rohit Pal Singh. I am a PhD student at University of Cincinnati. I am working in high performance computing lab with Dr. Philip Wilsey. So I'm in a TDO group working on persistent homology. So today I'll discuss about lightweight persistent homology calculations and we'll look at the basic flow of the code that we used to maintain at github.com. So this is a link to our GitHub repository. Okay, so you can visit it and look at it. So, so I'll be discussing about the basic LHF flows. So, and I'll first of all make you aware of the modes in which LHF can execute, and then we'll talk about the basic pipeline flow that our program went through. So, we'll look at the distance matrix, then neighborhood graph, and then Vittori strips calculation, and then the fast persistence. We'll also look at incremental persistence, which is kind of mix of means we generate RIPs as we go to higher dimensions while calculating fast persistence. So rather than computing at one time the whole Vittori RIPs complex, we compute it by dimension in incremental persistence. The LHF can execute in streaming precision homology and sliding window mode also. I won't be discussing that in this discussion, but if you want to look at it, it is there in the code base. Okay, so this is just a basic workflow that I've designed. So the one in the greens are a basic skeleton which we require to be executed for every LHF execution, right? So we need input data. So we need to read the file. Then we need to calculate the distance matrix for the data. So it is like distance between every possible pair of points, and then we form a neighborhood graph. We look into it, and then we form a complex Vittori RIPS complex. We have two options here: either to build a RIPS complex or Vittori RIPS complex in one go to expand it to the full dimensions up to which we want to calculate the precision homology, or we have another option to have it by doing it on the incremental basis, like we get it for dimension by dimension, right? So we generate it up to we get the dimension 1 simplexes, dimension 2 simplexes, dimension 3 simplexes, rather than getting them all being stored in one place at a one time, right? So this help us saves a big memory. Yeah, so this optimize our use of memory. And then we will see the execution algorithm for fast persistence. Yeah, so this is where we compute persistent intervals for features in the data. Yeah, so this is a basic skeleton which needs to be executed for LHF. Now, so for standard and fast LHF, we use this green ones, and then incremental is there's a little deviation here. Instead of doing complex generation at one time, we do it dimension by dimension as we go on to calculate the persistent intervals for each dimension. Then we have a reduced mode. Reduced mode means add two more extra steps. One is the pre-processing, and the last one is upscaling, right? So reduced mode, we have like we do it for when the point cloud or the data on which we are running precision homology reach the limits, right? So for example, RIPS are the state of the art program right now. It has its limits to up to which point the size of the point cloud it can execute LHF, right? Or it can compute persistent homology. So to kind of the reduced mode kind of sample took a representative points from the point cloud that are less than the original point cloud, and hopefully be preserves the topology of the space. So we use certain different pre-processing techniques to extract sample points or representative points from the point cloud, and then using those point clouds or centroid data as we run precision homology on that. So we using that point cloud as that centroid point cloud as a representative. We find its distance matrix, neighborhood graph, Vittori strips complex generation, and then the fast persistence, and then we just After getting the betis, we map the boundaries, right? The centroids that represents the boundaries of the betis, right? So, and then we use the partition of that centroid, boundary centroids, to find a point cloud where possibly the boundary of the feature lies, right? So the precise boundary. So we took the partitions, the cluster partitions from pre-processing step, and then we ran the persistent homology on the regional boundary partitions that we generated, right? So we'll discuss in detail how upscaling is done, but this is how the basic flow is for the reduced mode. So hopefully this upscaling is will scale or will produce the results that are significant, right? And then there is a distributed and parallel mode in which the LHF can execute. So we, rather than just executing LHF on the centroid partition, we execute in the centroid data. We execute complete LHF pipeline for all of the partitions that are there in for each centroid representative point, right? So this is what we call as we extract small features from these partitions because its maximum radius is scaled by Rmax into some scalar, where Rmax is the maximum radius for all the partitions, and yeah, so we use OpenMP and MPI for the distributed implementation. Yeah, so this is all we have. Then we pre-processing, data reduction by sampling. We have already seen upscaling is like result refinement by upscaling. I'm not discussing streaming, sliding window, and naive window as discussed earlier. Right? So merging of result is for MPI. So from all the different processes, we remove the duplicates and then keep the ones that are unique ones. Yeah. So for the distance matrix pipe, we have a sample input which store coordinates of the point cloud. It could be in any dimensions. Right now, I'm talking about 2D, but it could be in any dimensions. And then this is how they look like in the space. From this point cloud, first of all, we calculate the distance matrix. Like for 0, 1, every pair of edges, we find the distance. This is just a normal Euclidean distance we are using. And then there's a neighborhood graph. You insert all the vertices and the level 0 and a corresponding simplex, which is just a vertex itself and the index of the simplex. So for the level 0, it's very simple. The weight is 0 for all the vertices, and then we have like simplex vertex itself 0, 1, 2, 3, 4, and the index is like 0, 1, 2, 3, 4. So things are very simple here. Then we expand it to the level 1 where we have all the edges. So we have like 0, 1, 0, 2, 0, 3. So like here 0, 1, 0, 2, 0, 3, 0, 4, all the edges. 1, 2, 1, 3, 1, 4. All the edges will be here. So there are 9 edges total. So they are like 9, 1, 8, 6. So they are not ordered by their indexes. Like 9 comes here, 1 comes here, 8 comes here, 6. Rather they are being ordered in the ascending order of the weights. So the one which has the highest weight is on the end of the list, and if the weight is same, then they are ordered by simplex itself, right? So for example, 2 4 and 0 4, they have 4 and 4 equal. So we start from the last simplex index. Then we have 0 2, we have 2 as bigger. So if they had same weight, then this will come last and this would have come before this. But right now it has more weight, so it is in the last. I hope you get how we order the simplexes. Then you generate the Vittori strips to the dimension you want to calculate persistent homology up to. Right now I've extended to the full lattice, or you can say to the maximum dimension possible. And yes, so right now the points of just 5, so I was able to do it. But as number of points grows, this also grows exponentially. As we can see that the this is a kind of binomial expansion where we have like at level 0 we have n, and at level 2 we have like n choose 2, and at the level 3 we have like n choose 3, and at level this we have yeah, so things go weird. So like it is 5, 10, 10, 5, 1, right? So, and while computing the persistent homology, we just need one level at a time. So there is no need to generate a complex, full complex at a time. Means before computing the persistent homology, we can do it incrementally. So that is level by level generation as required by the persistent homology algorithm. So we can do it in a phases, right? So that's what we have it in persistent homology or incremental persistence. Let's talk about just introduction to the simplex indexing, how it is done. It's a bijection. So right now I have indexed the simplexes, vertices are indexed from 0, 1, 2, 3, 4, and then the edges are indexed from 5, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right now I have indexed them just to avoid the confusion because this 5 it doesn't start from 5. At each dimension the indexing starts from 0. So in essence it is 0, 1. So 5 is 0, 6 is 1, 7 is 2, 8 is 3, 9 is 4, 10 is 5, and 14 is 9, right? So if you, yeah, so the 14 is 9. So if you look at 9, it is an edge between 3 and 4. So 14 actually represent 9 and it is edge 3, 4. Let's see how we get to the 9 from 3, 4. If you look at the, this is a Pascal triangle using binomial expansion. If you look at 3, 1, 0, 1, 2, 3, 3, 0, 1, it is 3, 0, 1, 2, 3, 4, and then we have 0, 1, 2. 6 plus 3 is 9. Now, how do you get the 9 from 9? How you get 3, 4? We'll just do a reverse operation. For this we need number of points that are there in the point cloud. Right now we have like 5 points, and this is a simplex in dimension 1. So you calculate, so you know how many points are there. So 0, 1, 2, up to some dimension that we have. So right now we have 0 and 1. So to find the last index of the simplex, we choose ID such that this is maximized and is less than equal to the index. So 4 choose 2 is 6, which is less than 9. So ID is 4. That is the maximum possible number. Then we check for I0, but we reduce the 6 from 9 here now. It is 3. So you choose 3 because 4 is already done. 4 choose 1 is equal to 3, which is less than equal to 3, hence it is 3, right? 3 and 4. This is how you get it. You change this 2 to 1 and 4 to 3. I hope you get it. Okay, so now we look at persistent homology. How do we calculate it? Yeah, here I have just made a correction that how the indexing is done. 9 is 9 here. So we start from 0, 1, 2, 3, 4 again. So indexes are like this. So each level indexing start from 0. Now look at the persistent homology. So I have generated all the possible simplexes that are there for 5 points. They are from like, yeah, of course vertices are also there, 0, 1, 2, 3, 4. So they are like 0, 1, 2, 3, 4 are the vertices here, and 0, 1, 2, 3, 4 are the vertices there. So this represents vertices. Then these are the edges, 9 edges. Then there are 9 triangles. Then there are 5 tetrahedrons. Sorry, 10, 10 edges and triangles, and then 5 tetrahedrons and 1 4 simplex, right? Okay, so this is the boundary matrix looks like. So we have like the simplexes are sorted by their index right now. For each dimension they are sorted by index. Yeah, so sorry. So we now they are not sorted by weight, right? So this is sorted because they are all zeros right now. Means right now, or the vertices are all zeros. And then we have like this one is they're not sorted. 1.31, 1.04, 1.52 is the weight of the simplex 2, which represents 1 2. 1.71 is a simplex of is a weight of simplex 3, which represents 0 3. And here they're also they're not here sorted by, see this they're sorted by the rows are sorted by weights, but the columns are not. They are supposed to be sorted by weights also. Of course, dimension by dimension. So, for example, 1.31, 1.04, 1.52, they're not sorted. So, we need to sort them also. So, if you look at the next window, now I have sorted them by weights, by the cofaces weights also, and by the simplex weights. So, here you can see this represents cofaces, the columns here, and this represents the simplex. So, simplex and its coface. Okay. Now let's see how we get to the calculation of the persistent homology. So this is generally, folks, if you want to just clarify one more time, I will just give 0 is a simplex. It's a coface of 0. It's a coface of 3. It's a coface of 1 and 2. You want to look at what 0 is in this dimension, you can say it is 0, 1, 2, 3. 0, 1, 2, 3. You look 0. So you can say this is 0, this is 1, this is 2, and this is 3. And they represent previous dimension 0, 1, 2, 3, right? So they represent this one. 0 is this triangle, 1 is this triangle, 2 is this triangle, and 3 is this triangle, right? So I hope you get how this is constructed. Now let's see. So now we need to do the boundary reduction, boundary matrix reduction. This is the result after doing the boundary reduction. Now we'll see how we get it from here, right? So this is here, from here we started and we ended up here. How do we get to here from here? Let's see. Okay, so let's first of all, I want to let you know how this works. So we start with first simplex coface. We start from here. Dimensionally we start from here. We look for the pivots. Pivots are the one that lies to the top, which is the one in the column, right? So lowest one in the column is the pivot element. So this is a pivot. We look to its left. If there is nothing, then this particular coface is good to go. Again, one, there is nothing to the left. There is no pivot to the left of it, so it is good to go. 5, there is no pivot to the left of it, it is good to go. Now here at this 4, it has one pivot here, right? So we need to reduce this column. So to reduce it, we just sum up all the columns values in 4 and all the column values in 5. And then after summing all these values, the empty ones, we take it as 0, right? So when you sum it up, you take the modulo 2. 1 plus 1, 2, 2 modulo 2 is 0, so it becomes empty. 0 plus 1 is 1, 1 more 2 is 1, so here comes 1. 1 plus 0 is 1, 1 more 2 is 1, so here comes 1, 1. Now this becomes the pivot, this has already become 0, so 1 and 1, this comes again in its path. So we see, we again add it to the this particular word means 2, so now it becomes 1, 1 and 1, 0, and here we have like 4 is left with just 0 and 1 as its boundary. So you can say 4 is left with 0 and 1 as its boundary. Similarly, we keep on reducing this. So let me see one more example here. Okay, so after reducing this completely, let's see how we reduce this. It's basically the same procedure. For this column, there is nothing to the left of it, so this pivot stays. If we look at this pivot is to the left of it. So what you do, you add ones. So right now I will just show you how you add. So 1 plus 1, and then this, they become 1, 1, 1. This becomes 0, and this column, this becomes the pivot, and there is nothing to the left of it, so it stays. This is how it is. Now there is nothing to the left of it, this is also stays. There is nothing to the left of it, it stays. Now for this, we need to reduce it again. So we will see, just add up these two columns, and we end up having this becomes 0. Now this is a pivot again. So if when this becomes 0, this is the pivot, this is in its way, you add this column and this, all the values become 2, eventually they become 0. So this is how you reduce this column. And again, this is nothing to the left of it. It can't, means we are done with it. If you look at this, you need to reduce it. Same procedures you follow, and when you do the column operation, you keep track of it. For example, for a reduction of this, you add 1 to 2. After adding 1 to 2, you add 3 to 2. So 1 and 3 are added to 2 to make it completely reduced, right? So we maintain this kind of column operations. We'll see later. Right? So this is the complete reduced matrix. Now, how do we extract the persistent intervals from this? Right. So we look for all the pivots element that are there in the reduced matrix, and for the all the pivots, we see the weights that are in the last column here, and we'll see the weights in the last row here. These are the birth times and these are the death times. And if they're same, then they're appearing and disappearing at the same time. So we just don't report them. So for example, this one, it appears at 0 because 0 is here, and it goes to 0.95. So this is the first Betty we report. Then we have like 0 birth time, the death time is like 1.04. This is the second Betty, 0 birth time, and then 1.11 is the death time. 0 birth time and 1.12 is the death time. So we have like generated all these birth and death times. For this, we have like 1.52 is the birth time, and we have like 1.52 is the birth time. So it won't be reported because it has same birth and death time. 0, it is like 1.31 is the birth time and 1.52 is the death time. So here is the loop that we are talking about. So this is a loop 1.31, birth at 1.31 and death at 1.32. Rest all I think are same: 1.58, 1.58, 1.71, 1.71, 2.06, 2.06, 2.58, 2.58. And here also they are all same. So just these are the batteries that are being reported, corresponds to this is a loop that corresponds to 0, 1, 2, 3. How do you get the boundary points? So while this column we have reduced, and we look at the column operations that we have done, and we track from the column operations, the we extract the boundaries, right? So we'll see them. So this is a column operation. If you want me to let you know how do I get to 0, 1, 4, 5 as a boundary, 0, 1, 4, 5 as a boundary. So you see that this is a third simplex we are looking for, and this is in the dimension 0, 1, 2 dimension. 0, 1, 2 dimension, we are looking for the third simplex, right? Yeah, the third simplex. We look at the third simplex. It has an operation. So we have like it has reduction from 0, right? So and then 0 in turn is having a reduction from 4, right? And 4 in term has a reduction from 1 and 5. So it has, from this we get 1, 5, 4, and then 0. 0, 1, 5, 4. 0, 1, 4, 5. So this is how you get the boundary of the simplex. Yeah, that's it. So this column vector is important to get the boundary, to extract the boundary from the simplexes. Yeah. Now this is easier said than done, but what happens if the data is big, right? Just for the 5 points, the matrix grows to a size of 32 by 32, which is like 2 power 10. Right? This is 1024 in size. What happens with as the size grows? It just explodes, right? So we can't afford that much memory. So we need to find out a way to efficiently do this. So rather than storing a whole matrix, rather than storing the whole dimension matrix also, we just keep these three data. So it's like if we have a matrix and it's very sparse, right? What do you do? You don't store a complete matrix. You just make a sparse matrix representation of a matrix, which is just a linked list representation of the just the entries that are there in the sparse matrix with the corresponding indexes stored. So similar thing we are doing here to store. So because this is a highly sparse matrix, so we'll just keep the information that we need. So pivot pairs, and this is a V boundary matrix that we have, and the V columns is for just for the dimension for the simplex we are keeping, and we're generating the next pivot. So these are the data structures that we need. So the algorithm goes like this: we look for pivot pivot pairs. Like we'll see how you generate the cofaces also. So you generate the coface, and then you get the coface and then see if that coface is we treat that coface as a pivot and see if that simplex and the coface is already in the pivot pairs. If it is not in the pivot pairs, that means we need to add it to the pivot pairs, and then if their weights, the coface current pivot is the coface weight and the simplex weight are not same, you report the persistent intervals and you break. You're done with that particular simplex. And if they're present, then you have to reduce it and then repeat it again. So let's see how the algorithm works that we have in the LHF repository and the GitHub address that I have provided. These are the indexing that I just kept it here for your reference, just not to be confused or carried away by multiple zeros and ones in here, right? Across dimensions. Of course, right now they are just one. Okay, so we have a simplex. We start from the lowest simplex, which has highest weight, and we generated cofaces until an emergent pair appears. Emergent pair is when the simplex and its coface are the same weight, right? So we generate a coface by having, so for 6 is like 0, 4, you add 0, 3, 4. So this is the first coface. 0, 3, 4 is the first coface. That is 7, 0, 3, 4. 7 is the first coface. 0, 3, 4. It is emergent because 2.58 and 2.58 have the same weight. So if it is emergent, you don't extract this, right? So you don't report these cofaces because you're done. And when we have this coface, we treat it as a pivot. We treat this coface and this simplex as a pivot pairs. So we have pivot pairs like 0, 4 and 0, 3, 4, and we check. So 0, 3, 4 and so check for, so we have pivot pairs like 0, 3, 4 and 0, 4. They are the pivot pairs. We see if these pivot pairs are already present. No, we have just started, so pivot pairs are right now empty, so they are not there. So we'll just add them to the pivot pairs and see if the weights are different. We see that the simplex 0, 4 has 2.58 weight, and the its coface 0, 3, 4 also has the same weight, which is 2.58. So we add it to pivot pairs, but we don't report the persistent intervals. It is like it appears and disappears at the same moment. So we add it to the pivot pairs, we add it to the V column, and we add it to the next pivots, and then just done with it. Similarly, for 8 we generated cofaces. This is the emergent pair because 206 and 206 they have the same weight. So we don't report this in the reds, and we just add the 8 and its coface, which is 9. So 8 is 2, 4 and it's 9, 2, 3, 4. We add it to the pivot pairs, we add it to the column vector and v vector, and then we add it to the next pivots also. And similar thing happens, we look for weight if they have different weight. Right now and they have same weight, so we don't report uh, any of those. Yeah, interest. So something happens when we have like 3, right? So we have 0, 3 as a next simplex. We'll look for its cofaces. Yeah, this is the first case where the first coface in it is not an emergent pair. So it has a weight of like 1.71 and it has a weight of like 2.58. So We go generate the next cophase. It has a weight of 1.71. It has a 1. Now this is an emergent pair. So we don't report the next cophases, but we are able to report two cophases for the first time. So we made a heap for the cophases generated. So heap is like 0, 2, 3 comes here and then 0, 3, 4. And then you get the first item of the heap and treat it like a pivot. Check if it is in the list. 0, 2, 3 and 0, 3, they are not in the pivot pairs. You just add it to the pivot pairs and see if their weight is same. We use need to see 0, 2, 3 is like 2 and 0, 3 is like 3. So you have to see 3 and 2. So 3 and 2. So this column 1.71, 1.71. So their weight is same. So you don't report the persistent intervals and then you keep on repeating this. Again for the 7 you do this, you generate its cophases. So you add for here, you add 0, 2, 3 to the pivot pairs and next pivots and you done with it. Again for this 7 also you repeat the same process. It happens that you are not able, you just add a pivot, there are no reporting of persistent intervals here. You just add this to the pivot pair. The 7 is like 1, 4, you add 1, 4 and 1, 3, 4 are the pivot pairs you add. Then again you have like 1, 2 and 1, 2, 3 pivot pairs you add. Then you come to this column where we do have something interesting. So for the 0 simplex, it is like 0, 1. You generate all its cofaces 0, 1, 2, 0, 1, 3, 0, 2, 3. Yeah, means of course. Okay, so these are the cofaces because we are just looking for, we are doing it by adding highest index possible. So we are able to generate these three and rest of them are not being generated. So you look for the first one in the heap that is on the top of the heap, that is 0, 1, 2, and then you see 0, 1, 2 is there in the pivot pairs or not. It is not in the pivot pairs. You add it to the pivot pairs. You see if the simplex and the coefficient are the same weight. 1.52 is different from 1.31. So here you report the persistent interval. So dimension 1 birth is like 1.31 and death is like 1.52. And you extract the boundary by using a simplex 0, 1. So which is like 0, 1 is a simplex and then you look it for in the v vector. So how do you get? So you look 0, 1 is like 0 and then here 0 you look for what was the coface, sorry, so I was the coface is also 0. Yes, so the coface is 0, you look for it, and 380. Maybe I reported something wrong here. What was it? Mhm. Okay, so you look at 0, 1 and its boundaries using the column operation. So 0 is here. You look for it has 4 and 4 in turn has 5 and 1. So it has 1, 5, 4 as a boundary operations. So you just look at 0, 1, 2, 3. Okay, so you generate the boundaries like uh, for this you generate the boundaries like 0, 4, 5, 1. 0, 1, 4, 5. 0, 1, 4, 5 are the boundaries for this loop. 0, 1, 4, 5. Yeah. So finally we get the output. And then the limitation is like we can't go to much higher dimensions with lot of points. There's a limitation on the number of points we can execute higher dimensions. Simplicial complex size grows exponentially for like 100 points. The simplex grows to the like 2.53 into 10 power 30. I'm right now giving a number for the complete simplicial complex. If we generate it by level, then it is little bit better, or it's better, right? And then we can overcome this limitation by using sampling or reduced data to make a representative point cloud, and then and hopefully that preserves the topological features. You use clustering techniques or other sampling techniques to get these representative points, which preserves the topological data. And then after running a persistent homology on this reduced sampled data, you find the persistent intervals and then you refine them using upscaling. So for each persistent intervals that is reported by the reduced data, so we find its boundary points that are representative centered points, and then from those centered points we extract all the partitions of all the points in that particular partition, and then we take a union of all the partitions that constitute the boundary points corresponding to the centroid points, and then you compute the regional persistent homology on all those points, and hopefully you are able to refine the features for that particular region. And so this is how it works. First of all, pre-processing. This is the complete data. You just find the representative point and you reduce the data. After reduction, you compute the persistent homology on this data, and then you are able to report certain loops and words in the data into its loop. So let's see. Then you map this centroids data to the original point cloud, and then you add this partition, this partition, this partition, this partition, and this partitions to this particular feature, and you are trying to compute the persistent homology on this particular region to refine this better. Similarly, for this, you add all these partitions like 0, 1, 2, 3, 4, 4, and 5. So you add all these points, and hopefully they are smaller, means less number of points concurred by LHF. So after doing the regional persistent homology, hopefully we are able to refine the results, and this all about upscaling. And this is all about LHF, and this is the end of the today's talk. Thank you very much. I hope you enjoyed the video.